In the second video this week, we will be talking about georeferencing. And so, as you might remember from the first video, we may have data sets that do not have any type of Earth-based coordinate system. So in other words, there is no coordinate system tied to, say, a hard copy map that might be scanned into a computer system. Or sometimes we might download digital data sets that do not have any projected coordinate system with them. And when that happens, we have to go through a process called georeferencing, which is basically taking spatial data from, say, one data set or from data that were collected out in the field or from some other type of map that does have a coordinate system tied to it. And we're comparing the maps together to tie or connect Earth based coordinates from one image that does have a coordinate system to maybe an image or map that does not have that coordinate system. So this is very different than projection. Of course, some people get confused on that at first. But remember, projection is that idea of taking essentially 3D model of Earth in the way that we do coordinates like latitude and longitude and projecting onto a flat surface, so creating a flat map. This is very different because we're essentially tying a coordinate system from one data set that has coordinate information to a data set that does not. And this is very much a statistical process, as we'll talk about a little bit today. Whereas, map projection is a little bit more analytical. It's basically changing from either one projection to another or from a 3D type of system to a 2D flat surface. So for georeferencing, we might have a map that already has a coordinate system, some type of data layer we've been working with. Let's just pretend it's in the universal transverse Mercator coordinate system. But then we also have maybe an older map or some other older image, an aerial image that has no coordinate system tied to it. And we have to basically convert that image and make sure that it has the same coordinate system as another one. So one way you can do that is by essentially identifying control points. So we would identify points on the map that does not have a coordinate system and essentially connect that to some type of map or image that does have a coordinate system already set up on it. And so you'll see this process when I give a bit of a demonstration this week as well. And so, like I mentioned, georeferencing can be very important if you have, old historical maps, any type of hard copy that you need to scan into a computer system. That, of course, is not going to have any type of projected coordinate system attached to it yet, so you're going to have to do some georeferencing. It can also be important if you have old aerial photos, for example. And again, so the steps of this are pretty straightforward. Basically, you're identifying control points on the source map. So the map that has coordinates, you identify good control points on that map. And then you find the same exact locations on the map that does not have the coordinate systems tied to it. And you tie or match or basically connect those points together. And the system essentially is using a transformation equation, basically a linear model using polynomials, a polynomial type of linear regression model. And basically, when you get enough control points, you're able to then fix that map to estimate what the projected coordinate system would be on that map. And so the steps are basically tying that, estimating that equation, checking the error, seeing if there's any error within the model that you're building to make this georeference fit correctly. If there's error, you might have to remove some control points, add some new ones, recheck that fit, and you kind of run through this process over and over and over again until you minimize that error as much as possible. And so a couple things to kind of keep in mind when you're thinking about georeferencing. One, it's going to be important to have enough control points. You also have to make sure the control points are well distributed across the map and easy to identify. So for instance, if you're looking at an old image, there's lots of different potential options of places you might have good control points. Now, one thing that can certainly be used is a lot of times, say you have an old historical image, when you're comparing an old image, a lot of times roadways and road crossings can be a good control point, because when you compare that to, say, a newer image that you're going to tie the data to, you can oftentimes find that exact same location if the roadways still exist. Sometimes people might use things like, if the same exact building from, say, an old historical photograph is still in the same location in, say, a newer data set that you're working with, you could tie the corner of one of the buildings as a really good control point. But the idea here is you have to have very precise locations that are identical in, say, the old historical imagery to the same location to, say, some newer image that does have a projected coordinate system tied to it. And so you can kind of see on this map some of the potential control points might be these, road crossings here might be good ones. Like I mentioned, sometimes buildings can be good ones. What would not be good would be some type of landscape feature that could change, right? So sometimes people might say, well, you could use like a river or some type of area in a forest or something. Well, of course, those things can change over time. So what's really important, especially with historical imagery, is that you have to find something, usually some type of man-made feature that has not changed to be a good control point. So when we think about, trying to figure out control points, sometimes we have good information about control points. We have GPS location data that's already set up. Maybe there's information within a digital raster map that has the coordinate information, at exact locations. Now, it might also be possible that we have trouble finding some type of current map or image that has great control points. We might actually need to go out and collect GPS locations at exact spots where we can compare on the images that are the same between an old map and a new map, for example. So in other words, you might find some spots on the images that are the same, but then go out and collect exact GPS data to get very high quality accuracy in what the coordinate system, the X and the Y would be at that location. Then once you collect those data points, you can, do that process of georeferencing in the computer system. And so in the process of georeferencing, essentially what's happening is you're creating each point one at a time. So in other words, you're going into the map that has the source map that has coordinate system information, finding a point and clicking on it, and then finding that same exact location in the target coordinate system, the map layer that does not have any coordinate system attached to it. So finding identical locations, clicking once on the source coordinate system, then on the target coordinate system, then finding another point, a third point, a fourth point, a fifth point, and you just keep going and going and going. But there's a couple important things here. Once you get to enough points, the system that you're using, whether it's ArcMap or some other type of GIS software, is going to start estimating a transformation equation. And so once you start doing that process, basically what you end up with is a table showing each of those control points that you're creating. And so for those of you that maybe need to think about this a little bit in terms of statistics, this is a statistical process. Hopefully everyone out there is, taking statistics and will understand this a little bit. But you can imagine when you're basically targeting, say, the value. In this case, we're just thinking about one value, the easting value, and comparing that from the source map to the target map. So essentially what you're creating is a point, right, that is estimating some type of X value for the source map that has a projected coordinate system. And then that point that you create is also being matched onto the target map. And so as you start creating more and more points, you can essentially think about this like a linear model, right? So for instance, on the source map, we've estimated that we have a point of 1 on the source. That 1 equals roughly, I don't know, maybe 31 or 32 for the easting value of the target map. If we look at point 2 that we created, maybe it's this point here. That point has a value of maybe 3.1 on the source map. That 3.1 is roughly, 48 or so on the easting value. And so you can create a whole bunch of different points like this. And just like any type of linear model, basically you can set up a transformation equation. This is being done, of course, by the computer system, right? So a transformation equation that's estimating sort of the a line of best fit between all of these different points that you've created. And what you can kind of think about is when you do a line of best fit like this, there is always going to be some error, right? So we have these errors, which you might also remember are called residuals. So every time that there's a point, the point that's further away from this line of best fit means that we have slightly higher error. So kind of keep that in mind for a second. But eventually, when you have those points and you fit that line, you can develop an equation, so a transformation equation that can be used in the process of converting the image that in this case we're just talking about the x value, so you would do this for the x and the y, but it's basically converting all of those x values from the target map and making them the same as the source map. So basically converting or transforming that image that has no coordinate system and now converting it to the same type of coordinate system through this transformation equation. And so I'll just mention, on this that at no point on exams or anything like that am I going to ask you all about specifics of linear equations or anything like that. The important thing to know here is just the idea that by collecting these points, one from the source and one from the target map, you can begin to fit an equation that will allow you to then predict where that map should be spatially. Now, one of the main transformations that's typically used for this is called an affine coordinate transformation. It's a first order linear function. And so there are other ones. Basically, this is a first order, meaning a first degree polynomial. There are also second degree, third degree. So there are potentially other types of fits that would need to be done depending on the data set that you're working with. But most often, in almost every scenario that I've ever worked with georeferencing, you're able to complete a georeferencing project using this affine coordinate transformation. And so again, I'm not going to ask about specifics as far as understanding the linear equation, this first order type of linear function, but just understand that affine coordinate transformation is the most commonly applied approach. That it is some type of linear relationship that's being basically used for this type of transformation. And then importantly, and we'll talk a little bit more about that, is that you can, by fitting these using this transformation, you can essentially estimate the root mean square error. And so that's really important because by estimating that, we can get an idea of the amount of error that's taking place in our georeferencing process. And then just sort of one other thing to kind of think about is that as you apply some type of transformation, so you create all these different points, right? And we have an equation that's being estimated to fit from the target image to the source. What's happening is basically it's rotating that image. It's changing the scale of the image. It might change the skew or the direction of that image and sort of shift the image around as needed to basically apply the transformation to the image that doesn't have the coordinate system to make it match the image that does have a projected coordinate system. And so again, not going to ask specifics as far as how to calculate this, but it's important to understand that you can take the residual distances or the error and use a formula to basically calculate root mean square error. So I want to point that out just a little bit, that what I mentioned here, when you have sort of a linear type of equation, whenever you have these residuals here, right, the actual point estimates that you're taking, the further that point is away from the transformation equation or the linear model that's being predicted here, we consider that higher error. And so when we talk about root mean square error, what that means is you're taking each of these individual errors from all of the point estimates that you made during this georeferencing process and developing a total value of root mean square error. So what is the entire error from all of these different points that you're creating, essentially? And so take for example, if we had, say, a roads layer. So the roads layer here has Earth-based coordinates. We have a shape file, a vector data set with line data. That line data has a projected coordinate system tied to it. But the image in the background would be our target layer, a layer of an old historical image that has no Earth-based coordinate systems whatsoever. And so basically, the whole process of this is essentially finding locations on the image and from this road layer and matching those together or tying those or connecting those together in order to build that many different points for georeferencing to develop that transformation equation. So for instance, we might zoom in real close to a map somewhere on here and say, we know this is now the same location by comparing it. You would click on the source layer, in this case the road layer, and then match that point to the target layer, the image. So we know that this is the same exact cross section. I can click on the road layer, then click on the image here to tie those 2 point locations together. Then I do that again for another location. Do that for all of these different locations across the map, many different points that you're creating. And so again, you're creating each of these different points across all of the map that you're working with. And then the system is estimating the transformation equation as you're doing that. So it's estimating an easting and a northing value on this target layer based on the fact that we're tying that coordinate information to those different points across the map. And so in this example, if we have, say, these 5 different points, you can kind of see where those points would be based off of the control point and then the true location. So in other words, we have a true location, this point here, and then we have the point that we clicked as our control point on the image. And so basically, as you can kind of imagine, as this process is taking place, the transformation is altering the image. It's making it larger, making it smaller in scale. It's turning the image, it's skewing the image to make those locations fit together. And then again, the idea here is that by creating a whole bunch of different points, you'll be able to fit a transformation with a low root mean square error. And there are different rules of thumb for this, but most people think if you can get at least below a 5 meter, or it might be different depending on the units that you're working with, but usually we're working with meters. But a root mean square of less than 5 meters would be acceptable. So if we think about that, we have a table here. So remember, our table is showing each of the different points that we've created, and it's showing those residuals. Okay, so it's showing an X and a Y residual. And so if we take these one at a time, basically what you want are lower residuals, because a residual is the same thing as error, essentially, right? So remember, we're talking about in a linear model like this, a simple type of linear model. In this case, it's a first order polynomial type of model. But basically, we want low error. We want points that are well estimated along this line of best fit. And so when you end up working with this table, you've created, say in this case, 13 points so far. We can go in and we can say, all right, look, points 4 and point 1 and maybe point 9, these have really high values, high residuals. And so we might need to basically remove some of these points out. Now, right now, we have a root mean square of 16.4 meters based off of this table. So we might go in and just move out points 1, 4, and 9. We move out points 1, 4, and 9, we end up with 6.2 root mean square. But now we have another big one. We might want to remove point 10. We remove point 10 from the equation. Now we have a root mean square below 5 meters. So we're starting to get to an acceptable level of error based upon these points that we had. And so hopefully you can kind of get an idea of what this process is like. You're creating points on the image and tying those points to whatever data set you have that has Earth-based coordinates, going in and checking the root mean square error, removing any of those points that maybe we didn't do a very good job at estimating the location, checking the error, adding more points, going back in and deleting some until you get to an acceptable amount of error. And you say that I think this image or this map that I'm working with is now at a spot where we can go ahead and apply that transformation to develop the coordinate system onto it. And when we think about sort of some of the errors that might take place, why might we need to drop control points? Well, the control points, it might be human error. Maybe we just didn't do a very good job. Maybe the intersections that we looked at aren't exactly in the same location. They might appear that way on the map or the image that we're looking at, but maybe they're just not in the same exact location anymore. And so those points ended up not being good estimates for this transformation equation we're creating. So there could be really a whole lot of different reasons as to why the control points end up not being good ones. But the important thing is that you sort of keep running through this process of creating those points, deleting out the ones that have higher error, and just continue to work through that process until you get to an acceptable level of error. And so questions that I get a lot about this, or when you're sort of thinking about rules of thumb during this georeferencing process, one of the big questions is how many points do you have to create? I've heard different things. People say at least 12. Some people say you have to have more like 25, 30, or even more than that. It can kind of depend on, what you're georeferencing. But the main thing is when you get to a certain point of accuracy, adding a whole lot more points might not necessarily help. So, in other words, it might only increase the accuracy by such a small amount that there's not really a need to do more points. So typically what I've done is somewhere between 20 and 30 to start. And then I go through that process of deleting out those points that maybe have higher error involved with them and trying to end up with at least 15 or 20 points at the end. That's always seemed to work pretty well for me when I do that. But the other important thing to really think about is that the points that you're creating have to be accurate, but they also have to be well distributed. So if you imagine an image and breaking it into 4 quadrants, you want to make sure that points are well distributed within each quadrant. So let's look at an example of that. If we have an image and you imagine breaking this into the 4 quadrants, like I just mentioned, you basically might want to start by creating 1 point in one part of the quadrant, a second point in one of the other quadrants, 3, 4, sort of moving around and distributing points across the entire image, but making sure that each quadrant has multiple points in it. And so think about why that might be important. What we're talking about is trying to fit an image using this type of linear transformation, basically. So if I went into an image and only put a bunch of points into, say, this one left quadrant, what would happen is that the image that we're working with would be very highly accurate in this area, but would be very skewed in these other areas, right? So it's really important not just to make sure there's multiple points per quadrant, but to make sure that the points are well distributed throughout the entire image in general. So as I mentioned a little bit ago, a fine transformation is by far the most commonly used. It's unlikely you would really ever have to use a second or third order polynomial or these other types of adjust or spline transformations. These are different types of transformation equations that can be used. Now, last point I just want to make about this is we've talked about basically, we're creating these points, we're developing a transformation equation, and the idea is to try and get a lower root mean square error. But it's important to understand that just getting a low root mean square does not necessarily mean that the transformation was good. The RMSE, that error value that we're looking at, again, which is the error of all these different residuals from the transformation model that we developed, you have to really compare the images together to make sure that the fit's good, and then also make sure that the root mean square error is low. Now, the other thing I'll mention too is that if you were to use these other types of second and third order polynomials, you can actually, you typically will get much lower root mean square errors. And so that's why most systems, and it's usually recommended to use this affine first order polynomial, is that you don't necessarily want the system to show you a low root mean square, but then actually not have as great of accuracy. These other types of transformation equations are really for more problematic types of images that you might be working with. So that's kind of another thing to think about as well. So again, what I would say is if you're going through this process, the root mean square is very important. You want to make sure it's low, but you also want to go in and just eyeball and look at things and say, is this road matched up well with the image itself? Because if you were looking at, say, an image like this, a low root mean square, but the images aren't aligned, you know that's a problem. So it's sort of a little bit of eyeballing, making sure everything looks good and is aligned and that the image is set up correctly, or the map is set up correctly, and making sure that the root mean square is low enough too, to make sure that you're happy with it. And so that's the last thing I'll mention about georeferencing. Again, I'm not going to ask you all on exams or anything about, running a linear model or how to do any of those equations. The main thing I want you to understand is that the overall process, the steps it takes to properly georeference an image or a map into a GIS. Also, just kind of trying to understand, not the exact mathematics behind it, but at least understand that it is a statistical process using typically a fine, transformation equation, which is basically a type of linear first order polynomial equation. And really, I hope you'll understand that idea of the root mean square error. So this idea of using a value that takes into account all of the different errors or residuals from each point that you're taking, what that overall error is based upon the line of best fit from that transformation that was used. So hopefully that all makes sense. And when I do a little bit of a demonstration of georeferencing in class, that'll hopefully help out as well in understanding this process. But that'll be it for georeferencing. So if you have any questions about any of this material, please don't hesitate to reach out.